Hi, welcome back to Low to High Level. It has been a minute since I worked on a real video because I was just not happy with the CPU we designed in the past. During the last two videos, we designed and built a CPU completely out of logic gates. Now that's great to say that we can do it, but there are a few trade-offs when you design stuff with engineering, and the trade-offs that we took, I am very much not happy with. For example, we limited ourselves to 8 bits and 256 bytes of RAM. Now, that could be a lot of RAM in the 1940s, but in today's modern world and with what I want to take this project to, it's not enough. So I'm going to go back and we're going to redesign it. And with our new design, instead of taking it directly from Boolean logic, we're going to skip that step. And we're going to go straight to making an emulator. I've already done that, so the end of this video will just be a time lapse of me making the emulator. But until now, we can go through a little bit of our design. This is my terminal right here. So emacs-nw doc/arch. Okay, so here's what our architecture now looks like. We have a 32-bit bus and 32-bit data, and we have a few ALU operations. We can add, we can AND, we can OR, we can XOR, we can rotate to the right, and we can rotate to the left. For instruction types, we have an R-type instruction, which is dealing with registers. So it'll have 3 zeros followed by the negative. So whether we set the negative, whether there's carry in, data. So this should be the type of operation. These are flags of some sort. And these, we're negating B, which is our B register. We're setting the carry in. We have 3 types of operations, which are these up here. We have the out register. We have the A register and the B register. This has actually changed a little bit because of my implementation, whereas we're now doing that. We have an immediate type, which says, okay, if the first 3 bits are 001, followed by a 5-bit register, which is where we're storing, and then 29 bits of data. And this will just be set immediately into the register. Then we have a memory operation, which will read from memory. And memory read says, okay, we are inputting. So this is the register we're inputting to. And then we are storing it into this register. So this input register would store the address that we want to, and it would store there. Memory write is similar, except we have the address here and the data here. So this is the data we want to write. This is the address we want to write to, and they're all both stored in registers. We have 2 types of jumps. We have a jump relative, which has a condition and then a short of the relative location. And we have a jump register, which has a condition followed by an address of the register. And if these conditions are met, then it does. So we have a few different conditions. We have an absolute, which means that we will always jump on this case. We have 0, which is if the 0 flag is set, carry if the carry flag is set, overflow if the overflow flag is set, neg if the negative flag is set. Then we have registers, which R0 is always 0. R's 1 to 30 is general purpose. R31 can be used as a stack pointer, but it technically can be used as general purpose as well. So that's the general idea of it. And if I go look at source/main, this is our main program that runs our emulator right now. We're setting our flags here. We're setting our address pointer here. And here we are generating a few different commands because we don't have an assembler. We don't have a way of writing stuff, and we don't have a way of reading from files yet. So what we're doing is we are loading into address 1 the value 16. We're loading into address 2 the value 15. And this is saying, we are going to add the values in registers 1 and 2 into register 3. And then here we're moving the value in register 3 into value 4. Here we're loading into register 5 this value, which is an address. We're loading into value 6 this value here, which is H. And then we are writing to a specific location, which is the location address 5 and the value in address 6. And then we're doing the same thing here. So this write next function is just writing to our ROM, which is our read-only memory. So we're writing that data to the ROM before we run the program, and here we are running our program. We don't have a halt system. We don't have a way of handling that, so that's what it handles for now. And then after it runs our predefined number of commands, it will run that and print. It'll basically print out the register information. So if we run this, we can run make, and then target touch main. It runs, it prints out H, and then it prints out the values in each register. Register 0 is always 0. Register 1 is 16 plus 15, which is 31. That got moved into register 4. Then we loaded that address into register 5, and we printed, this is the \n. So that basically runs our very basic program that we're generating via code as opposed to by an assembler. But that's fine, because we don't need an assembler to run our code. We can do it manually. So nano source slash what main. Let's see. So yeah, we have that. And ideally, we'd be able to create some machine code that we write by hand and input it to this program, which we could, but that would be a lot of effort. And that is our topic for the next video that we'll do. So this is our first step in making that ALU and making our CPU design an emulator. Then we have to move up a layer of abstraction. And our next layer of abstraction is going to be an assembler. So that'll be the next episode. Thanks for watching. Bye.